See that? And that? And that? And that? They're all engines used to generate thrust and combat drag. As we talked about in a previous video, every aircraft, including spacecraft, experience drag through the atmosphere, which is the air refusing to watch giant metal birds cut straight through it without picking a fight. To combat air's drag, we need to push straight through. We've quickly covered the three types of thrust in a previous video, but today we're going to dive into more detail about how these powerful pieces of engineering propel us forward, upward, or wherever you want to go. We've swiftly covered how propeller engines generate thrust, but how do they even spin in the first place? There are three ways to spin a propeller: internal combustion engines, electric motors, and turbines. Internal combustion engines, or ICE, not this ice, that ice, run by using small controlled explosions to push a piston downwards. The piston is connected to something called the crankshaft, which in automobiles would be connected to the transmission, but for aircraft, it spins the propeller. This form of spinning the propeller is most commonly found in old aircraft like the P-51 Mustang, or in classics like the Cessna 172. Electric motors in aviation are mostly split between two types: permanent magnet synchronous motors, or PMSMs, and brushless DC motors. A PMSM uses permanent magnets on the rotor and electromagnets in the stator. When alternating current flows through the stator, it creates a rotating magnetic field that pulls the rotor magnets around. The rotor spins at exactly the same speed of the magnetic field, making the rotor highly efficient, precise, and favored for aircraft. A brushless DC motor also uses permanent magnets on the rotor, but its controller energizes the stator coils in a sequence that creates a rotating magnetic field. Sensors or software determine the rotor position, so the controller knows which coils to power next. This eliminates the need for brushes, reducing wear and increasing efficiency compared to traditional DC motors. Electric aircraft are less common but are slowly growing in popularity, some professionals even stating that they're the future of aviation. But we'll get into more detail about that in a future video. Using turbines to spin a propeller is called a turboprop engine. Turboprop engines are basically jet engines that use the energy created by the jet to spin a propeller. Turboprops are best used for large aircraft with medium range, like the Lockheed C-130 Hercules and the ATR-72. Most of the thrust comes from the propeller rather than the turbine. But wait, how do jet engines even work? Most aircraft today use jet engines for propulsion, but like everything in engineering, it has its own categories: turbofan, turbojet, ramjet, and scramjet. But before we dive into how these differ from one another, we first have to understand how jet engines work. In the intake stage, air enters the engine through the intake, which slows and smooths the airflow. During compression, the compressor, a series of rotating blades that compress the incoming air, raises the air's pressure and temperature. This prepares the air for efficient combustion by sharing a dense oxygen supply. During the combustion phase, fuel is injected into and mixed with the compressed air, then getting ignited. The burning fuel-air mixture expands rapidly, creating high-energy gases. And finally, at the exhaust stage, the high-energy, fast-moving air spins a turbine at the rear of the jet engine, which powers the compression phase before being spat out of the back at really high speeds. Now, turbofans are really similar to turboprops. They have a giant fan right before the intake phase, pushing large amounts of air to generate thrust. The air that bypasses the compression and combustion is simply called bypass air, while the air that does suffer through the rest of the stages is called core air. One of the key differences between turbofans and turboprops is that a little more of the turbine's exhaust contributes to thrust, making it more efficient for higher subsonic speeds and altitudes, which leads to its widespread love for international and intercontinental airliners like the Boeing 787 or the Airbus A330. Turbojets are turbofans without the fans. They rely solely on throwing exhaust air backwards as fast as possible. Simple, powerful, and fast. It's the most effective for high subsonic to supersonic speeds, making it perfect for modern fighter jets, with it and its cousins being used in basically all modern fighters, ranging from the Sukhoi Su-27 flanker to the Lockheed F-35 Lightning. Turbojets haven't seen any use in modern airliners, with a few exceptions like the Supersonic Concorde or the Tu-144. Then you have afterburners, the coolest part of modern turbojets. When you don't have enough thrust and still want to go faster, you mix in and burn more fuel into the rest of the burning hot, uncombusted air. Ramjets and Scramjets are similar but a little different. The thing is, they basically don't have any moving parts. So look, Ramjets rely solely on the air compressing itself, using a specialized inlet, as seen on the BrahMos missile or the Lockheed D-21, back to subsonic speeds before combustion. You heard that right. The aircraft must first be supersonic before the ramjet can start. This is why you almost never see it in aircraft. Ramjets are most useful between Mach 2 to 6. But what if you want to go faster? Scramjets are the version of ramjets where the engineers gave up on slowing the air to subsonic speeds, and found out it still works. Like ramjets, scramjets use shock waves formed by the fast-moving air to slow itself down. But for scramjets, the air air doesn't go subsonic. It stays supersonic, between Mach 2 to 4. They're also more complex than ramjets. They must be able to inject fuel, mix it with the air, ignite it, and let it burn before it leaves out of the rear. Mind you, the air is flying by faster than most fighter jets could ever go. Having a functional range of Mach 5 to 15 plus, it's practically useless for airplanes, and only being used in experimental aircraft in the United States, Russia, China, and India. All of the engines we've discussed so far require air to generate thrust. But what if you're in a vacuum with nothing to pull in or push away? So again, there are different types of rocket engines, that being chemical, nuclear, and electric. Chemical rockets are the most common and split between two types: liquid state, or liquid propellant rockets, and solid state, or solid propellant rockets. Liquid state throws liquid fuel, mostly liquid hydrocarbons or hydrogen, and ignites them, then controlling the expansion through a nozzle to produce the maximum and most efficient thrust at the altitude. This is necessary because atmospheric pressure differs at different altitudes, and so the rate of expansion will differ. Okay, so solid state rocket engines follow the same idea, but instead of using supercooled liquid fuels and oxygen, they use a mix of solid fuel and oxidizer. They are much simpler and easier to understand and manufacture than liquid state engines. But the only problem is that they have their own oxygen supply mixed in with them. And if you haven't caught on yet, you can't choke it out. Once a solid state rocket engine is ignited, it's ignited and will burn through every last bit of propellant. Putting it in water won't work. Changing the pressure won't work. Not even a vacuum can stop it. So that's what led engineers to invent the hybrid rocket engine, which uses the best of both worlds, a liquid state's controllability and a solid state's simplicity. It works by using solid state fuel but without the oxidizer, and is controlled by the injection of liquid oxygen as the oxidizer. Nuclear rocket engines are the blur between efficiency, effectiveness, and just a downright safety hazard. They're when engineers were willing to do anything just to get a raise during the Cold War. So again, there are multiple types of nuclear rocket engines, but we'll only go over the three most common and realistic. The first of which are nuclear thermal rockets, or NTRs. They're the equivalent of shoving a nuclear reactor inside of a rocket, but instead of heating water to generate electricity, the reactor heats liquid hydrogen, which is then expanded through a nozzle to produce thrust. And yet again, there are more types of NTRs: solid core, liquid core, and gas core NTR, where the name indicates the state of the uranium core inside of the reactor: solid, liquid, or gas. Solid core NTRs use solid uranium rods. They're the easiest to use but limited by the melting point of uranium. But don't sleep on them, because they can still fire hydrogen at an impressive 8 kilometers per second. Liquid core NTRs use molten uranium. Same concept, but allowing much higher temperatures. This method almost doubles the hydrogen expulsion speed, but is much harder to contain the radioactive material. Gas core NTRs are the same thing, managing higher temperatures, doubling the speed of the exhaust, and containment is a much harder problem now, with gaseous radioactive materials and fission products. Nuclear electric propulsion, or NEP, is again shoving a full nuclear reactor inside of a rocket, harnessing the energy as electricity and using that electricity to produce thrust. Once again, you've got three more types: ion thrusters, Hall effect thrusters, and magnetoplasma dynamic thrusters. Ion thrusters accelerate ions using electric fields. Very efficient, but produce low thrust. Hall effect thrusters work using the Hall effect. Can you imagine that? They use electric and magnetic fields to accelerate ions and generate thrust. Hall effect thrusters have a higher power density but a slightly lower efficiency. Finally, magnetoplasma dynamic thrusters work by ionizing a propellant gas, such as lithium, xenon, or argon, and accelerating it using the Lorentz force. They are some of the most fuel-efficient engines, counting the engines that do use fuel for propellant, and the most powerful NEP, but it is still incapable of producing enough thrust for high-speed maneuvers. Last but not least, nuclear pulse propulsion, or NPP. Imagine sitting in a spacecraft, but instead of spitting off anything or igniting a flame behind you, you detonate literal nuclear bombs. NASA's Project Orion tested this during the Cold War. It promises extremely high thrust and potential for interstellar missions, but it faces very significant safety, environmental, and political challenges, such as, why the hell would you want that? If you've watched this far, thank you so much and congratulations on your new knowledge. I hope you enjoyed this video and learned something new. If you did, then you can like this video and definitely subscribe. Be careful with your explosives and have a nice day.